all the time. It allows me to determine when one community is more diverse to another. That tells me if impacts, when they're likely to occur, where it'll have a greater impact, right? Okay. So again, what's the take-home message from this then? For any starting point of species richness, right? If I have the same species richness between communities, H diversity will increase with species evenness. So that basically means if I have 10 here and 10 here, if it's more even over there, that one's more diverse, okay? And the opposite is true too. For any given species evenness, if it was all even proportions, if you have more species, you're more diverse. The trick is, what if one has less species and greater evenness, and the other one has less evenness and greater species? Now, which one's more diverse? That's hard intuitively to wrap your head around, and that's why the math is important, okay? Because I've been in plenty of communities, and like, I have no idea intuitively which one's more diverse. More species there, less here, but this one's way more even. Well, the mathematics will help me sort that out, and they'll tell me which one is more diverse than the other. All right, good. Let's talk about disturbance in communities. We talked about disturbance in terms of distribution when we dealt with the chaparral, right? And it's an event that removes organisms and frees up resources. It can be big, it can be small. My mom lives in Hawaii. They're kind of pooping their pants right now. Why? Because there's a big hurricane sweeping in. Hawaii hardly ever gets hit with hurricanes. Hawaii is this little tiny pinprick in the middle of the Pacific, right? It's like hitting a bullseye. You know, it's almost impossible. And because of the way the wind conditions go there, it has a tendency to swing hurricanes up and around, not through. But because of changes in the climate, we're seeing shifts in the trade winds, and guess what it's doing to the hurricanes? It's swinging them not past, but now up and in, not up and out, and that's problematic. So the track of this thing is going right towards Hilo, where I used to live and have friends, and it's going to swing past Hilo on the Big Island, and the trajectories, the cone, can hit anywhere, swing out, which would be wonderful, or wall up Kauai, which looks like what might happen, or maybe even swing past in between Kauai and Oahu. That cone of transition is pretty crazy right there, right? And they're not well set for hurricanes over there because they typically don't get hit with them. So that's a big disturbance event. Walking on the grass was a small disturbance event. Right? You didn't think anything of it, but if I was the bug that you stepped on my head, and I was the grass blades that you all screwed up, I'd think it was a big deal, right? All right, so communities vary in terms of their disturbance. It can be really high, it can be really low, it can be frequent or infrequent. And so there are middle grounds too, where you have intermediate levels of disturbance. Well, we've talked about COML a lot, correct? COML has come up with one of the basic, most fundamentally sound ways to look at community structure that can be applied to every biological community on the planet and has some type of validity typically. And so this is the basic idea of it. When disturbances are very severe and they're very frequent, you find that the community is made up of things that are only good at colonizing disturbed habitats. Okay? So their structure is get in, get out before the conditions get bad, right? If once you have a disturbance, get in there, take advantage before it happens again. We refer to those as an R-selected species, and they typically have high reproductive rates. What does that little R refer to again? You remember? That's the per capita growth rate, okay? So R-selected species have high reproductive rates, high population growth rates. The opposite of that is when disturbance is really mild, population density builds up really high, and that means to survive in it, you're right near carrying capacity. Well, if I'm right near carrying capacity, I better be a good what to survive there? I better be a good competitor because I have to fight everybody for the resources that are scant, yes? So if that's the case, this would be referred to as a K-selected species. What does the K stand for? The carrying capacity. So K-selected species are really good competitors. R-selected species are great colonizers. When you plot this along a frequency of disturbance from low to high versus species diversity on the y-axis, you actually end up with a plot that looks like this. It's a nice unimodal shape, a hump-shaped relationship. Notice, where disturbance is low, who survives? K-selected species. Where disturbance is high, R-selected species dominate. Where are they both found together? intermediate levels of disturbance. So here's an example. Here's the oak tree. An oak tree, once it gets to a certain size, can compete any other type of plant. It's big, it's thick, it's invulnerable to fires for the most part, natural fires that are burning regularly at a normal fire cycle. It's almost invulnerable to insect predation because of its thick nature of its leaves and its bark on the trunk. Once it's there, it outcompetes everything. It'll shade out everything, it'll take the water, everything. A dandelion sucks at competition. Everything can outcompete it, but it has one edge. What is it? It's the first there, and it can take advantage of the new resources, pack it on to biomass, produce offspring, and be dead and gone before anything even is there. You see dandelions, you strip some grass, you open a plot, what's the first thing there? Weeds. Weeds are R-selected species. Dandelion is a nice example of an R-selected species. All right, this species can completely eradicate that one. But why in the middle do they coexist? Because this one has no resistance to what? Disturbance. All its energy is put into what? No, not growth. Competition. They grow super slow. Hundreds of years in some cases, right? 100 years for some of the big ones. So they grow super slow because all their energy is going into outcompeting every other. They have no resistance to disturbance regimes. Okay? The fire cycle gets off skew a little bit, boom, they're gone. They burn out, all right? This one, all about energy into growth and reproduction, none into competition. So if I add a little disturbance to the environment, what will it do to the abundance of this? Will it drive it to extinction though?
No.
No. A little bit of disturbance will just drop the abundance. And when I drop the abundance of that, it leaves room for who? That to coexist because they're not being completely outcompeted. Intermediate levels of disturbance allow inferior competitors, which are typically R-selected, to exist because the disturbance regime allows them into the habitat, creating coexistence and higher species diversity. All right. Does it work? It's a great theory. Does it work? Yeah, it works. It works in a lot of places. And so here's a nice one right here locally. This is the Elwood Boulder Field. If you guys ever been to Montecito and you go to like Hammonds and places like that, the surf breaks there, you go to the Biltmore. There's a big intertidal boulder field right there. This is where the work was actually done. This is work done in the late 70s, early 80s by Wayne Sousa, who's now a faculty member at Berkeley, was a graduate student here. And so his observation was this. Boulders that were intermediate in size had a lot more species of algae than either the big boulders or the small ones. Well, that sounds like a great place to test the intermediate disturbance hypothesis, right? Why is that? Because little boulders, when the waves hit them, what do? They just flip all over the place. But a big, gigantic boulder, it doesn't move at all. And then middle-sized boulders, they flip intermediately, right? So every time you flip, is that a disturbance? Yeah, if I land upside down, I've been disturbed, okay? Because I'm dead, basically. So it's a disturbance event. So what he wanted to test was, when he looked across the spectrum, small boulders had what? Higher low diversity? Low, because they were flipping all the time. Big boulders had what? Higher low diversity? Low, because there were only what there? K-selected species. On the little boulders, who was there? Only R. But on the intermediate sized boulders? Both. Now this is what he did. He took a little boulder, I shouldn't even call it a boulder, he took a stone, right? And he glued it onto a larger rock. As soon as he did that, what happened to the diversity on the small stone? It instantly went up, and you got more species, even though the surface area was smaller, there were more species still on it. So what had he done? He'd altered the disturbance regime to make it more stable. But it wasn't completely stable, it was intermediate because it still flipped occasionally, and it went up. So the results, he glues the small boulders to a larger one, species diversity increases. On the largest boulders, like that, one thing dominates. It's this thing called Gigartina, and it's this nasty kind of encrusting algae that takes over every surface on the stone. Everything. If you disturb them, it takes forever for them to come back, but they're on boulders that never get disturbed. So it takes like a 50-year storm or something to flip a rock of that size. So when plotted, what, lo and behold, is that a model match? Perfect model match, okay? Worked great. So what's the take home here? Species diversity was higher when the disturbance was moderate. The stability of the stones was influenced by their size. Their size, therefore, influenced the diversity that you found on the stones because of their stability. All right? Let's take a look at some other hypotheses to explain the diversity of communities. This is the diversity stability hypothesis, first developed by Alton in the 50s. And this idea was simple. The more diverse a community is, the more likely it is to be dampened in terms of fluctuations, right? It's basically resilient to change. And the effect of disturbance would be a lot less in a community like this. If the disturbance, if you have a less diverse community, a disturbance will have a big impact on you, right? So this is really seen in agricultural crop fields. If I get a pest outbreak in, say, a monocultural crop like the soybean over there, is the impact small or big? If I get a pest in that versus this, which is a natural meadow, which one has a bigger impact, the disturbance of the invasive pest? Soybeans. In the soybeans. An invasive pest in soybeans can wipe out 90% of your crop within a matter of days. You'd hardly even notice it in that thing over there. Okay? So the diversity is somehow enhancing the resiliency of these communities to invasive pests and disturbance. And you can think of an invasion as being a form of disturbance. So here's an extension of that. These were experimental plots that were created by Tillman. This is a nice classic experiment from the mid-90s. And in this particular case, it was a long study, 11 years, 207 of these big kind of plots like this in the field. 11-year study is quite unique. I told you guys what the typical study length is for ecology. What do you think it is?
1 year.
The typical study is actually less than 2 weeks. The typical field of study over one thing ranges from 3 years, but actually less than that. It's like 2 years, 1.5 years, and at most to about 4.5 years. That directly is in correlation with what? Those time spans.
Funding.
Well, funding for sure. But where's the time coming? That 1.5 and then the 4.
School.
It's school. What kind of school?
Graduate.
It's grad school. It's if you're a master's degree, your study typically takes 1.5 years at most. If you're a PhD student, it goes for about 3.5 to 4 years. That's it. And that's where the vast majority of our time is. So 11-year study is crazy. Hardly ever see it. Well, how was he able to do it?
Funding.
Funding that was able to hire multiple grad students in sequence year to year to year, and then undergraduates to support that work, right? That was funded too. And that allowed, kind of remember how you built a life table? Remember the age structures that we were able to build? Same basic idea. So you can generate a long-term ecological study as long as you can fund multiple generations of graduate and undergraduate students to do it. And that's what he did. So in this case, he measured the biomass of each species in each plot every single year, and he calculated how much of that community biomass varied from year to year, depending on the amount of species that were in a plot. They're a pretty cool study, too. You see how they're kind of divided into those squares? So here's the problem. If I want to measure diversity, I have to get in those plots and stomp around. But what's the problem when I do that? I kill everything. I am the disturbance, right? So he had a pretty ingenious way to do it. He had these structures on wheels, and so the wheels would go on either side of the crop, and then on top was mesh. And so the undergraduates would lay down on the mesh, and then they would roll the thing across the plot, and you count as it got rolled. And so you never had to touch anything. That's pretty cool, right? So it's kind of a low-tech solution to a real serious problem in terms of experiment. So this is what he found. As the species richness in the plot went up, the variation in the biomass went way down, which means that they were more stable over time, okay? The more species that were there, the less variation you had in biomass year to year. If I had 10 species and I had a dry or wet year, there was less change than if there were 2 species. But here's the difference. In 10 species, if you lose one, there's a drop, but what can instantly happen? What's that? Another one fills the space. But if I have 2 species and one drops out, I've lost how much of my plot? 50%. It's hard. What if I have 1 species and it's lost? It's done. It's gone. So the extra species add resiliency to any kind of disturbance, change, events. So that's the real conclusion here. Higher diversity increases the community stability. You grow resilient plants because they fill in for any accidents that may occur with other plants in the community following an environmental change. Not all plants in each plot will be sensitive in the same way to changes in the environment from year to year to year. All right, let's talk about succession. Succession is basically the transition of species composition over time. There are two types of succession. There's primary succession, and then there is secondary succession. Primary succession means you start with bare soil, sterilized soil, nothing living in it. That's a rarity. Where do you find that?
After disturbances?
What's that?
After
Not just any disturbance. If I kick the rock over, is that primary succession?
No.
I didn't sterilize anything, right? I killed a lot of stuff, but I didn't sterilize it. So where do you find something like that?
Major disturbance.
Not even a fire will do it.
Volcano?
Volcano will do it. Brand new fresh rock from the surface. A nuclear bomb will do it. And asteroid and meteor strikes will do it. Okay? Severe kind of exposure to those type of elements. But it's not a common thing. The far most common thing is secondary succession. You disturb something, there's always some kind of colonists, some kind of survivors who are left behind, bacteria, whatever it is. There's something there. Okay? That would be secondary succession. You start with a subset of what was originally there. There are successional pathways that you find. So the first to come in are selected species. They get in there quick and they occupy it, right? Later on, they get replaced by case-selected species that are good competitors, exist in their carrying capacity. So you typically have a transition. Disturbance, R selected to K selected, another disturbance. Where will it reset it to?
R.
Back to R. Now, if it goes all the way back to the beginning and starts with R again, that's referred to as a cyclical succession. Cyclical succession. You start in one place, it ends up circling back to it. Directional selection means you just go in one way and you stop. So if I basically had a disturbance, was R replaced by K, and then K just sat there and never changed, that's going to be what? Cyclical or directional?
Directional.
That's directional. Let's look at a study. Before I do it, let's talk about invasion. I'll come back to this. Invasive species are a huge problem on our planet because we ship this stuff all over the place. Invasions are much more common and successful in disturbed habitats. We disturb habitats every day. We are the #1 disturber of habitats on the planet. So we're good at disturbing, and invasive species are good at filling that disturbance that we've created. So invasive species disrupts communities by colonizing it and then dominating it, causing the loss of native vegetation. It's a massive thing for us in terms of economics. So bioeconomics are a huge problem. So for instance, this is the zebra mussel up here, $70 million per year minimum. We have kudzu, it's found in the southeast. That's a vine-like creeper that used to be an intact forest, which is now dead. Minimum $500 million per year, just in eradication control alone, besides the loss. This thing here, Burmese python, South Florida, released from the pet trade. People love the snake when it's this big. They don't like the snake when it's 8 feet long and it's choking you to death, right? So what do? Instead of getting rid of it the way they should, which is euthanasia, they let it go in the backyard. It does fine in the Everglades. It grows into this friggin' beast here, which eats everything, including small children, all right? Not pleasant. This thing over here is the nutria. It's basically a gigantic rodent. It's a big rat. It came in from South America. You find it along the waterways. It's incredibly destructive to riparian vegetation. It can strip it bare. So every known way to get rid of these things has been tried. Almost they always fail, unfortunately. Their impacts are they altered community composition. They altered the disturbance regimes. When we think about invasion, it comes as a series of events. So this was by work from a professor who used to be here as a colleague at one time and then departed for Europe. And so this is the basic process of invasion. It starts with an introduction of something. It somehow gets there. You moved it over in the ballast of a ship. You brought it over as an ornamental tree and let it go. You bought your snake from Indonesia and then let it go in the backyard in Florida. And then it becomes established. It makes a home there and it can survive in that particular habitat. Once it survives, it starts to reproduce and spread. Once it spreads, then it can cause impact, and that's when it disrupts the community as a whole, and that's what you're left over with. Let's take a look at an example that puts this all together. So this is actually a study that I worked on with a colleague of mine. They're back east now. And so this is with an invasive species of tree called the tamarisk, which is right up there, which is very common in the southwest of the United States. And it's an invasive tree. It was brought over as an ornamental tree. people released it, and then what happened was it got loose and started to take over waterways. And it's extremely good at what it does. So what happened in this case, let's talk about the natural situation. What we're left with today is replacement of native riparian vegetation, which is the vegetation that grows along the river, by monocultures of this crop, which excludes everything. All right, everything. So naturally in southwest rivers, they look like this. They're pretty dry most of the year, and then they get water and they flood, and then they're wet for some of the year, and then they dry out, and the cycle is repeated over and over and over again. So when you look at species that are adapted for living next to these rivers, they're well adapted to this flood pulse. It floods, it dries, it floods, it dries. And that cycle is very regular year to year to year, and that's how they're developed. So their abundance goes up. When the conditions are good, the floods drive them down a little bit. It's a predictable disturbance. They're well adapted for it. Their numbers come right back up to the next year, right? Up, down, but it's very small. Nice density-dependent response around carrying capacity, right? That's how it works. However, we are building everywhere in the desert, and we need what? We need water. And we do not want to lose that water to a big flood. So what we do is we dam the river to regulate them and maintain the water. So what does that immediately eliminate? The flood pulse. Now all of the life cycles of those plants are all screwed up because they're no longer pulsing, okay? And they're evolved to deal with the pulse. So what happens is you immediately begin to reduce their abundance because they are no longer being triggered by natural environmental cues. And now Tamarisk is introduced into the system from release from plant nurseries and places like that, and it gets loose. And it loves that kind of habitat because it lives in a similar habitat for where it comes from in China. And so basically, it starts to take over places in the habitat. It becomes introduced into the habitat. Now what we start to see is its numbers start to come up as it becomes established and starts to spread, okay? And as it starts to spread, it begins to outcompete native vegetation for space and resources. And then something very interesting occurs. It starts to burn. So the area that it comes from in China originally is much drier than the areas that we are seeing these native vegetation plants at, and it combusts and acts as fuel. So fires start. Now here's the thing. Our native riparian vegetation is not adapted to burn. You hardly ever see fires that burn down to a river's edge because there's too much moisture in the vegetation for them to combust because they're sucking it all from the river. Tamarisk, on the other hand, dries out and will burn like a big torch. The problem is if you start a fire down there and burn it, and if you burn a native tree, it's dead. It will never come back because it has no defense against fire. But the tamarisk is well evolved for it. So if it burns, what's the first thing back? More tamarisk. So that fire generates the complete and utter dominance of tamarisk in the riparian corridor so that there is absolutely nothing left. So at first it was cyclical. You went up, you went down, right back to the start again. You start with R decay of native vegetation. We influence it by damming. That allows the introduction of tamarisk, which does not do well with the flood pulse. It will get wiped out. But if you get rid of the flood pulse, it now becomes introduced and established. Then it starts to self-propagate, burn, and as it burns, it drives down the native species. What you have changed is a situation which was cyclical, R decay of native vegetation, and you've driven it in one path now. It's no longer cyclical, it's directional, where you've gone from native vegetation to a monocultural tamarisk, which are all case-selected species. And that's it. That's all you got. Never goes back anymore. Even after a disturbance, you're right back to where you were. There's no cycle there anymore. There's no transition to anything else. It's just tamarisk. Yes?
So was tamarisk introduced before or after the damming?
It was introduced after the damming. Okay, the damming went into place, and then tamarisk was able to get a foothold. So tamarisk was around, right? But when you dam the rivers, as soon as you dam them, you get rid of the flood pulse. And that was what kept tamarisk out of the rivers. All right? So there was around, it was in the nurseries and everything like that, but it couldn't get an introduction in the right place. How do you rephrase that? It couldn't get established in the right place, okay? Yes?
Has like the succession of releasing more water at night from dams like proven to reduce?
Dams that have scheduled releases that are more normal have less tamarisk infestation. Okay? So it's an interesting phenomenon, right? So again, what's this succession of invasion? Introduction, establishment, spread, and then impact. Exactly the same phenomenon. But we drove it, right? And that's the problem. What's the problem when you have this? It's a monocultural organism, all one thing. None of the native plants are there, they're all go extinct, and all the animals that were dependent on them go extinct as well. It's not a great idea, okay? I was telling you about the beetle I was working on. The idea here is you introduce a beetle that eats all that stuff. And once it eats it, it damages it enough to allow who to come back? Native vegetation, as long as you modify the flood pulse again. All right. So we're going to shift now to the very last section of the class. And we're going to talk about species interactions within the community itself. And so competition is really important. We talk about it time and time again. We want to know how species interactions within a community affect the diversity that you find there. And so niche relationships are really important. What's a niche again? The ecological space. All right, very good. So remember that it's a bubble, but I'm going to take one axis of that bubble to talk about. And so this axis, I'll give you an example of birds and seed size, okay? So the amount of resource, this will be the amount of seeds used, and then the niche breadth would be the size of seeds, from small to intermediate to large. I have two species of birds, species 1 and species 2. Species 1 eats primarily what size seeds? Small and intermediate. And then species 2 is eating what?
Moderate to large.
Small and, that's right, big and intermediate. All right, so when I look at this, where's there the most competition for seeds?
Intermediate.
Dead center in the middle for intermediate sized seeds. Is there competition for small seeds?
No.
Oh, think about it. What? There is intra-specific competition for small seeds. What about the big seeds? There's intra-specific competition for big seeds. But what about for intermediate sized seeds? There's both. There's intra-specific competition and interspecific competition. That's not good. When I lose that energy to competition, it can't go into what? Reproduction. That's exactly right. The wider the average niche breadth is of a species, the fewer species I can pack into an axis. Right? Because they're so big, they're overlapping. There's no room to fit any other species in there. So what happens is, where that extinction is occurring is right at that overlap. That's where competition is most intense, and competitive exclusion will take place right on that area of overlap. So here's the trick. How do I avoid that? I don't want to be right there. Competition is too intense. What should I do? I should specialize on what? Big or small seeds and avoid that. Certain individuals will be better at it just by sheer chance alone because of mutations that they have in morphology, behavior, or physiology. They'll be better adapted to eat small seeds. Because they're better at grabbing the small seeds at a higher volume, they'll pass those traits on to their offspring. So over time, what will happen to those curves? They will separate apart. That's exactly it. So, over time, I can be left with something that looks quite like this. This is species packing. The narrower the average niche breadth, the more stuff I can fit in, right? That's coexistence being partitioning the resource. Now I mean small, really small, kind of small, intermediate, semi-intermediate, semi-big, and really big, right? Well, how do you get from that to that? Well, it's just with the discussion that we began right here. So, if you're over here and you're over there on each side of the curve, I'm only dealing with intraspecific competition. So I'm going to produce more offspring than individuals who are competing for the intermediate sized seeds, because they're putting way more energy into that, not babies. So over time, individuals will spread out because they'll have better adaptation for those seeds on either side, and it will spread those curves apart. That reduces the overall overlap. Okay, that's great. These guys are doing both better, but what have I just opened up when that happens? When you spread sufficiently apart, what's now liberated?
The center part.
I should be eating in the middle now again, right? Because hardly anything is competing for the middle. So a good species, either an invader, right, or something that happens to plunk down there by chance, or some interesting mutation that allows it to go back and feed on intermediate seeds again, or behavioral change, can give me an organism set that'll plunk right down there, another species. And now I got 3. But as soon as that happens, what happens to the area of overlap again? Now it's massive. So what are they going to do? Spread out again. As soon as they spread out sufficiently, what will happen? They'll drop in again. And so